Now, I'm going to do this same thing one more time. I'm going to open SPSS, which I think is open already. Let me see if I can get to it. Yep, here we go. I'm going to open SPSS, and I have taken a lot of the data that we're working here in a couple of different files, and I put them together into a single file. Here, this one over here is time elapsed. That's my column. That's what I'm comparing. Now, in SPSS, I can say, I want to analyze this through a t-test and compare it to a known value. That's my single sample t-test. I know the population mean I'm comparing it to. I'm going to go up to Analyze, Compare Means, one sample t-test, exactly the same thing that we just did using Excel and pencil and paper. I'm going to go to one sample t-test, and I'm going to say, okay, what's the test variable I want to work with? But it happens to be that time elapsed, right? And notice that it gives us a test value. It's asking us what value you want to compare it. What's the mean of the other population, which is known? What do you want to compare it to? And that was 65. So I'm taking exactly the same data, and I'm going to analyze it using SPSS. I'm going to click OK. And now my output window pops open back here. And let's see what I get. I get let's see if I can't bring this up here so you can see it. Okay, so let's see what I get. Well, look at this. I get a t-score of negative 2.5, 2.6 basically. I don't remember what we got before, 2.7, but I had rounded off. So it's about the same t-score, negative, as we spoke about, as you noticed, Sarah. Right? It's a negative number, 19 degrees of freedom, and it tells me something called a significance, two-tailed significance. Well, what it's telling you there is the probability of getting a t-score that big on either side, you know, adding up the probability of its being positive 2.5 or negative 2.5, the probability of getting that big a t-score because of the difference in the two means is 0.018. The probability of being outside of that range is 1.8%. In other words, the probability of rejecting your null hypothesis, a lot of people call this the p-value, the probability of rejecting your null hypothesis and being wrong, making an alpha error, is 1.8%. Nice thing about SPSS is that instead of just using the t-table and telling you whether it's less than 5%, it actually gives you a real hard possibility. So in this case, this is less than 0.05, so we reject the null hypothesis. Had the probability of being wrong been bigger than 5%, in other words, the t-score wasn't big enough to give us a probability of being wrong if we reject the null hypothesis of less than 5%, then we would have failed to reject the null hypothesis. This is the same result that we got with the confidence interval, same result we got by mechanically doing one single sample t-test. And but this gives us an actual probability that we can compare to 5%. This is bigger than 5%, we fail to reject. Smaller than 5%, we reject the null hypothesis. So we got the same result here as we got before, except we got it with a lot less pain and a lot less trauma, and we got more information than we did before. This part over here is 95% confidence interval, two means being different. Mu1 minus mu2 is equal to 0. This SPSS calculates that, and it says, well, the mean difference between these two groups is 5.7. In other words, 65 minus whatever, 59.7. That's where that came from. And it says that the confidence interval for the difference is -1 to -10. So our null hypothesis was the confidence was that the difference was 0. So this is actually another kind of test where you can see that we're 95% sure that the real difference, is not does not contain 0, -1 to -10. So we can also reject the null hypothesis that way. But you really only need to do it this way. You don't have to worry about that. But SPSS just gives you so much data to work with. Okay, so now let's move on to another version of this. Okay, I'm going to go back to my stuff here. Let me bring this back up. Spread this out again so we've got a little bit more room to work with. Okay, and I'm going to advance it to the next table. Okay, I just want to show you the output here. This is the output that we just got. Okay, and the important thing here is that this table gives us the mean, for our group, the standard deviation for our group, that's the only one we have, we didn't have it for the other group, the standard error of the mean, and it does a t-test. SPSS always does a t-test, even if the sample size is 954. It always does a t-test, even though it's virtually the same as a z-score. Okay, so it tells you what the t-test is, tells you what the degrees of freedom is. This is the important part. If this is less than 5%, right, that's the level of error. If this is less than 5%, reject the null hypothesis. If this is 5% or more, we fail to reject the null hypothesis, right? Because we haven't proved with 5%, with less than 5% chance of being wrong, if that's greater than 5%, that the two means are different from one another. Okay, so that's what we're looking for on those tables when you print them out. Okay. Now, let's take a look at another possibility. You got another possibility is you have a proportion. Okay, and I'm only going to do a single sample proportion test because I think mostly that's what we covered in class, but you can do two proportions. There is a formula for doing two proportion sample, two different groups, comparing two different proportions together. I'm only going to do a single proportion right now. Okay, so let's say that you take a you're gonna analyze voters' attitudes on a certain proposition because you want to know whether it's going to pass in November. Okay, well, you say to yourself, okay, well, 50% is what I need to achieve in order for this proposition to pass. Okay, so now you go out and you take a sample of 100 people. Out of that 100 people, 54 people are for it, and 46 people are against it. So what is your point value for the proportion of people in your sample that are for this proposition? Well, your point value is going to be equal to, I'm going to call it P cap, is going to be equal to 54 out of 100 people, or 0.54. Okay, so now let's take a look at that. P cap, I put the cap on there because that's our proportion for our sample. I don't know the population proportion P. That's unknown because I would have to, that's going to happen on election day. Election day, everybody's going to vote. We're going to know what the population proportion is. But all I know is from my sample that it's equal to 0.54. So now you want to say to yourself, well, is that result significant? Can I say with 95% certainty, in other words, 5% chance of being wrong, alpha equals 0.05, can I say with 95% certainty that that's different than 50%? Okay, so now I'm going to say to myself, okay, well now in order to do this, I'm going to do I could do a confidence interval, or I can do basically a t-test. I can say P cap minus P that I'm assuming for that we need to pass this over the standard error. Okay, and that's going to be equal to my t-score in this case. Okay, so now let's take a look at the difference between the two. Instead of means for our point estimate, now we're using proportions for our point estimate. And our standard error gets calculated a little bit different. We know that, right? Standard error now for our sample is going to be equal to P times 1 minus P over N, and we take the square root of the whole thing, sample size. Okay. Now, we also know that because both sides of this, there's 54 people on one side of this proposition, 46 people on the other, both of them are larger than 15. Both samples are, so overall, the sample size is greater than 30. So I'm going to justify that to say, well, that's a z-score, not a t-score. So I know in order to reject the null hypothesis, my z-score has to be bigger than 1.96. Because that's the z-score, that's the difference in standard errors that I need to say that there's less than 5% chance of being wrong on a two-sided test. Okay, so now let's see if these two things are really different. So now, 0.54 minus 0.50 over my standard error. Let's calculate that now. That's going to be equal to 0.54 times 0.46 over 100, and we're going to take the square root of all of that. Okay, let's get our calculator out. Point 0.54 times 0.46 equals, oh, excuse me, something happened there. Let me clear this. 0.54 times 0.46 equals that divided by 100 equals this, take square root, equals about 5%. I'm going to round that up for my purposes. You don't round, I round. You round at the very end, about 5%. So, well, I'm saying to myself, gee, that's 0.05 down here. So this is 0.54 minus, that's equal to 0.54 minus 0.04. Z-score is equal to 0.04 divided by 0.05. Well, that's only equal to let's see, 0.8, right? 0.8. Well, that's nowhere near the 1.96 that I need to say that the proportion 54% for this sample size is different than 50% of the people needed to pass this resolution, right? So I fail to reject my null hypothesis that P1, P cap, or P for the population is greater than 50%, is not equal to 50%, right? So I could have done a one-tailed test on this also, because, maybe I could assume that since I got a higher number, I just want to test whether it's higher, not lower. But that would have been a little bit of a cheat. So we like doing two-tailed tests instead of one-tailed tests because they're a little bit more rigorous than the others. Okay, so you're doing really kind of the same thing here as you're doing with means, except you're calculating the standard error differently.